Swayam Prabha. Digital India. Educated India.
Welcome to Concrete Technology, Module 1, Lecture 1. We shall be discussing about cement production and composition in this lecture. Of course, to start with, we will just introduce concrete as a material, because it is a course on concrete technology. So, general outline of our discussion would be concrete material, components of concrete, and also we will just mention concrete as a composite. At the end, we will talk about cement, the production process and its composition. Now, what is concrete? Perhaps you would have seen concrete or also a little bit studied about it. Concrete is made up of components such as aggregation of stones, which we call as aggregate, embedded in cement mortar, that is cement sand mortar. In its hardened state, concrete is aggregation of stones or similar hard material embedded in what we call cement sand mortar. The aggregates in normal concrete forms the skeleton matrix. It is about 60 to 65% by volume, and rest all is 25% is the paste. Now, paste means cement and water that combines to paste. So, this aggregate when we are talking of, it is the large aggregation of stones, sand, etc., put together. 1 to 2% voids are usually there in normal concrete. It is required that the aggregate shall be inert and strong. Inert means should not be reacting with anything, and it should be strong. It should be strong so that it can carry the load, so that it can carry the the concrete can withstand forces. Ingredients of concrete, therefore, if we look at ordinary concrete or normal concrete, it is made up by mixing inorganic material known as cement. I said cement sand mortar. So, this is cement is one of the component. Water together with cement forms what is called paste, and then natural sands or stone dust, like something like this, as we can see, stone dust or natural sand. And in addition to that, we will have coarse aggregate, which quite often could be crushed stones or natural uncrushed stones themselves. So, therefore, concrete is generally normal concrete or very conventional concrete is made up of cement plus water These two makes paste, sand, which we call as fine aggregate, could be sand or crushed stone powder, and then stones, which forms a coarse aggregate. So, that is generally the concrete, normal concrete, generally the normal concrete. But modern concretes, if you look at it, it is not only these 4 components, but it has definitely 2 more components. So, modern engineered concrete has additional ingredients other than these 4 components just mentioned, right, and these are chemical admixtures. These are chemical admixtures, like there some of them are called accelerators, set retarders, water reducers, etc., and these ones are added to the concrete system during production in order to improve the performance of concrete either in fresh state or in hardened state. We will discuss about them later on in details. Mineral admixtures, this is the other kind of material which goes into the concrete, sometime even in cement making, and these are fly ash, silica fume, rice husk ash and other pozzolana or similar other material. So, as we can see, modern concrete is not 4 component material, but 6 components material. So, modern engineered concrete is actually 6 components material rather than 4 component material, all right. Okay. Chemical admixtures, as I mentioned, they are for specific property or performance enhancement. And mineral admixtures, they do improve long term strength, durability, performance. So, therefore, these 2 admixtures are must in modern engineered concrete. Of course, manually produced concrete, non-engineered concrete may not include this, but an engineered concrete definitely includes these 2 items as well. And using this admixture, it has become possible to obtain high strength materials, modern high strength and high performance concrete, right, and you can design the concrete as you like. So, this is what the concrete is. Now, there are lot of advantages and disadvantages of concrete, a few. The advantages are lower life cycle cost. It is relatively a cheap material, right. I mean cheap, relatively cheap, and a material that is used for construction purpose is used in very huge quantity. Therefore, it is a requirement that a construction material be cheap, and concrete of course is cheap. It has what we call low life cycle cost. Now, life cycle cost means not only that initial cost, capital cost is low, initial production cost is low, but its maintenance cost, future maintenance cost during its service life period is also low. It can be molded. You can mold into any shape that you like. Concrete can be molded. It can be molded to any shape that you like. It is robust. What it means is that, robustness, what we mean is that where I need massivity, it can provide that massivity. For example, if I have a structure, let us say I have a structures like this, a dam or a retaining wall. Now, horizontal forces if acting onto it, then it must have sufficient resistance against sliding. It should not slide, it should not slide along this direction, it should not slide, or it should not overturn, because these forces will have a tendency to cause it to overturn. So, it must have sufficient resistance against sliding. So, resistance against sliding, sliding and overturning, that must be there, and this you can get from concrete. This you can get from concrete, not for, let us say, it is very difficult to make a retaining wall or a dam out of plastic, or let us say even steel. Steel you can, but steel is not very common, but concrete can provide this kind of robustness. Concrete can provide robustness, and you can design it for desired property. You can design it for desired property. Whatever property you want, you can design it for that. It is a composite. Now, a composite is a material, as you know, is made up of number of materials or ingredients, which when combined together, when they are the final material is produced, it has a property different than the original material used in its production. So, concrete is also a composite, and composite concrete you can design by varying the proportions of ingredients or changing the ingredients themselves. You can design for desired property, not of course very versatile, but quite versatile, because it has got two weaknesses. One is it has got low tensile strength, and other it has got lower ductility. Now, ductility is a property by virtue of which the material exhibits a large amount of deformation prior to failure, and such large deformation ensures warning prior to failure. It does not fail suddenly, but particulate system bonded by cementing material, as in case of cement, we have seen that it was aggregates which were bound together in a mortar matrix, and if you go further, the mortar itself is made of cement paste in which we have sand. So, concrete is a composite. First, aggregates are embedded in mortar matrix, and in mortar sand is embedded in cement paste, and if you go further down to finer sizes, you will find cement paste itself has got different solid components as well as pores, etc., etc. So, it is a composite, and it is actually particulate system bonded together. So, one can call concrete as a chemically combined ceramics also. Chemically combined ceramic, a composite. Its composite, and it's actually composites, if you look at it, its composite form varies from scale to scale. At the scale of structures, it is almost we quite often assume it to be macro homogeneous, but if you go to slightly finer scale, you will find aggregate and mortar. Go to still finer scale, you will find it is paste and sand, hardened concrete I am talking of, and in the paste itself there are different solids which we will discuss sometime later on. So, it is composite and at each scales its composite nature of the composite varies, and it becomes more and more complex as we go to the fines, and properties of the final product actually is dependent on the micro level composite as well. Anyway, we will talk about this sometime later on, but what we understand is, since a particulate system bonded by the cementing material, such material do not exhibit large ductility, they fail suddenly. So, it is brittle. So, these are the two disadvantages, but it is quite advantageous from other point of view. Now, to take care of this aspect, we actually put in steel reinforcement, and you use reinforced concrete as a composite, or we pre-stress the concrete. Therefore, when we use concrete as a structural material, we rarely use it alone, except for in gravity dams or massive structure where we use mass concrete, and reinforced concrete or pre-stressed concrete, which are again another form of composite. They are quite versatile, and therefore, we can design them almost for whatever property we desire. So, that is why this statement, and that is why concrete is the most popular material in the earth. In fact, it is water, the human being consumes possibly water, and next material is concrete. In fact, cement is next to water consumed by human being, right. So, this is a very popular material, that is because it has got all these advantages. So, concrete and concrete composite systems, some of which we will be discussing, like it is not only one type of material, it is varieties of material today. Modern concrete, there are varieties, and we can classify them something like that: normal strength concrete, high strength or high performance concrete, ultra high strength concrete, or some composite, special composite having very high strength. We will discuss some of them at the end of our at the last module. Then fiber reinforced concrete. Then there is something called densified with small particle, which will possibly come into ultra high strength system. Macro refractory matrix, which is again an ultra high strength system, and reactive powder concrete, which are again ultra high strength system. All this we will discuss in details. At the moment, I am just introducing you the name of this concrete or cement based composites. We will discuss about them at length sometime at appropriate time. Then there is something called polymer concrete, polymer modified concrete or polymer cement concrete, self compacting concrete, and some more self compacting concrete, roller compacted concrete. So, some more additional ones are self compacting concrete, roller compacted concrete, etc., and we will discuss them at appropriate point. In fact, in general, if we look at concrete, the binders can be, there may be many binders, like I said, polymer concrete. So, therefore, it is also not a cement based composite, but it is a concrete of some type, or polymer cement concrete, where polymeric material is added almost like an admixture. So, you can have different types of binders, because you can have varieties of cements as well. The matrix is a skeleton I am talking of. Here it is a matrix is the skeleton, that can also vary, and I can put varieties of fiber reinforcement to obtain the composite. So, therefore, concrete, there are a lot of choice are available to me in terms of the binder, in terms of the matrix, in terms of the fiber, and like A is a material which has got this binder, this matrix, and maybe somewhere here is a reinforcement, because I can use varieties of fibers in the system. We will discuss about this special concrete sometime later on, as I mentioned. So, this is just to give an overview of the concrete before we start with the actual discussion of cement. Right. So, let us look at now cement. A little bit of history. You see, mankind used lime and silica for quite some time. In fact, first use of lime as a construction material, as reported in literature, they actually found out, Professor, one of the articles by Professor Aaron Bentour, that somewhere some of the people from Israel, they could trace the first use of lime, something to prehistoric time, possibly 7,000 years from now. Lime was used as a construction material, right. If you look at Roman civilization, they used lime and volcanic ash, right, because Italy there are volcanic ashes available there and they use them. So, lime and volcanic ash. In medieval India, people have used lime and surki, lime and surki. Surki is a material which comes out from brick kiln. When you burn the brick, then there are fine dust which settle down below. You know, when you burn the brick, when you burn the brick in a kiln, so there will be fine dust. This is the brick kiln, let us say, and fine dust will settle down at the bottom. This is called surki. Then lime and surki was used in India also, largely as a binding material of stones to produce concrete, like concrete is an artificial stone. So, masonry, in masonry construction or something of the similar kind. So, bind the stone masonry, lime surki was used. Now, what is surki or volcanic ash? If you look at volcanic ash or surki, they are nothing but clay, I can say clay mineral heated to high temperature and cooled rapidly, right. In fact, clay, volcanic ash or surki are nothing but clay minerals heated to high temperature and cooled rapidly, cooled rapidly. Cooled rapidly. Now, what is ash chemically or clay minerals? Essentially, these are clay is silica, alumina, some amount of iron, etc., magnesium, carbon, all these are, but main compounds are silica, alumina. So, what we are doing? You are heating up silica and alumina and then cooling them rapidly. Now, this results in formation of amorphous silica, not crystalline, amorphous silica. And in amorphous material, in crystalline material, atoms are arranged in regular order. So, they are at lower potential energy, relatively stable. Amorphous material, on the other hand, atoms are all haphazardly arranged and it is less stable, can react, provided physically this material is fine, so that large surface area is available for reaction. So, when it comes to surki or volcanic ash, these are clay material heated up and they are cooled rapidly. In fact, there will be some amount of energy trapped into it, chemical energy trapped into it. It forms an amorphous material, and if it finds a conducive condition, it can react and dissipate that chemical energy. So, amorphous silica, fine amorphous silica can react with lime and can give you hard material, solid, hard solid like stone. And this is what was observed by, this is what was utilized in Roman time or even in India, Now, calcination of lime together was silica obviously was the next step. So, in case of the earlier ones, this material volcanic ash were known as pozzolans. We will come to that again sometime later on. Now, this material together with lime in presence of water forms a hard mass, almost like stone. Okay. So, as the surki with lime and water forms hard mass. Now, these are reactive silica basically, the surki or the pozzolan or the volcanic ash. So, the reactive silica can react with lime in ordinary temperature, but lime and silica, if you combine them together and burn it, then that could give rise to a product which can react with water itself, because in lime surki reaction you had lime, surki and water. Now, lime and surki you put together, heat them up and form into a compound that can react with water to give you similar hard mass. So, that is the idea of cement, and actually the most commonly used cement is called Portland cement, patented by Joseph Aspdin in England in 1824, and this when mixed with water hardens. Since it is mixed with water and hardens, we call it hydraulic cement. Portlandite is a stone name, and from that it got the name of Portland cement, right. So, this is what is the cement. So, therefore, in this one basic raw material used in this manufacture is calcium carbonate, the lime, and the calcium carbonate which you can find in limestone or chalk, and silica and alumina and iron oxide found in clay or shale. So, the difference here is you are putting them together and heating it up and doing of course something more, is just a little bit of processing, further process, we will come to that. And in case of lime and surki or lime or pozzolana, lime and volcanic ash, you are actually using a reactive silica together with lime, get similar kind of product. So, Portland cement is this ordinary Portland cement as we call it, it is actually produced from lime and clay or shale. So, basically essentially you are using the silica, alumina and iron present in clay or shale to get the cement. There are two processes, well there are, I will not say they are rare, one process called wet process, which is now not used much. So, you have to essentially mix up lime and silica in appropriate proportion, and wet process was used where they were made into slurry, and you get a homogeneous mix of the two. So, in the wet process one would have got better homogeneity, about 40% would have been the water in the slurry, but then when you heat it you have to drive out that water, therefore, energy used is more. In dry process the technology improved in the second half of last century, and therefore, 1980s or 1990s onwards you do not find wet process anymore, it is mostly the dry process. So, modern practice is dry process. Essentially what you got to do, you got to mix lime and silica or clay and limestone in appropriate proportion, and you got to grind them to fine size. grind them to fine size, and amount of grinding will of course depend upon the raw material. Generally grinded up to 10 to 30% retained on 90 micron sieve, 10 to 30% retained on 90 micron sieve, 10 to 30% retained on 90 micron sieve, and this homogenized, then you mix them up, grind them, this is called raw mill, and this homogeneous raw mill is introduced into the top of a preheated tower, and this passes through a series of cyclones, pre-calciner as it is called, passes through cyclone separator, series of cyclone separators to pre-calciner, it is called pre-calciner vessel. There it is subjected to flash heat, sudden temperature rise of 900 degrees centigrade in gas stream, and some of the carbon dioxide from the lime is driven out, because you know calcium carbonate is lime, which you heat would result in calcium oxide, carbon dioxide. So, calcium carbonate, some of the carbon dioxide, majority good lot of carbon dioxide is driven off here, and this material then is allowed to enter into a rotary kiln and then heated to 1500 degrees centigrade, which causes partial melting, and the tumbling action of the kiln converts it into granular material called clinker. So, this clinker, because it will melt, when you heat this material it will melt, form solid solutions, and because of the tumbling action they form into granular material, and this is called clinkers. So, this is called OPC clinker. The clinker is then cooled, grinded with gypsum to obtain ordinary Portland cement or Portland cement. One issue is important right at the beginning, just let me introduce here. Since carbon dioxide is, calcium carbonate breaks down to calcium oxide plus carbon dioxide, therefore, you are producing carbon dioxide. In addition, you are using energy for heating, and when you use energy for heating, you might be using fossil fuel in some form or other, and people have actually calculated that about 0.74 to 1.25 or 26 tons of carbon dioxide is produced from 1 ton of ordinary Portland cement production. So, but on an average you can say that 1 ton of OPC produces 1 ton of carbon dioxide, which will be an important point of discussion sometime later on, because with the concern of global warming and greenhouse gas emission, carbon dioxide is one of the greenhouse gases along with water vapor and methane, etc., etc. This issue has become very important, that cement produces carbon dioxide, a greenhouse gas. Therefore, OPC clinker consumption should be minimized, or it should be used as judiciously as possible. So, that is why at the beginning itself I just wanted to point out here, which we will be discussing sometime later on at some appropriate point of time. Right. So, diagrammatically if I look at this production process, you will have limestone coring, maybe some other raw material you might be adding as fluxes and things like that to control the clinker formation temperature, clay or shale, this is the other one, and this two together both of will be grinded and blended to get an uniform mix of the two, and all these are mix together to get a final blend, which I can store somewhere, have a raw mill which I can feed now to the preheater or pre-calciner, where I will have cyclones and it will get heated, followed by some of the carbon dioxide will be removed. After the preheating, then it will go to the burning kiln, where once the product is formed, this will be mixed with gypsum and grinded by finished by grinding. So, this is what the production process of cement clinker looks like, right. This can be then stored, this can be then stored in appropriate manner. If we look at the kiln, where the feed enters, this is dehydration zone, where water will move out if there is any free water at 50 degree to 100 degree centigrade. At 600 degree centigrade, clay decomposes, right. All exhaust gases go out through this. So, therefore, water vapor will move out along this direction. The heat is supplied from here through by burning process, there is a burner, so through which you actually supply the heat. This zone is somewhere here is the 1500 degree centigrade, this is inclined a little bit, so that, and this is rotary kiln. So, it is rotates. At 600 degree centigrade, clay will decompose, then limestone decomposes. This is the calcination of the limestone will take place within this zone of 600 to about 1200 1300 degree centigrade, and this decomposition of limestone results in carbon dioxide, which will go away with the exhaust gas. Then formation of C2S, one of the compounds in the cement clinker, that takes place, and C3S forms at somewhat higher temperature. This is called clinkering zone, and then you cool it, the clinker goes out, cooled to about 60 degree centigrade or so, and then later on you can mix up with gypsum, very small amount of gypsum, and grind it. So, therefore, if I summarize the cement production process, cement is produced by burning calcium carbonate found in limestone or chalk, right, found in limestone or chalk, and silica and alumina and iron oxide found in clay or shale at about 1500 degree centigrade, 1500 degree centigrade. The material sinters and partially fused to form clinker. The clinker is cooled and ground to a fine powder with some gypsum, resulting in ordinary Portland cement. Well, one important point is that India is the second largest producer of cement after China at the moment. In fact, we have been second largest producer of cement for quite some time, with a lot of infrastructure construction going on all across. China and India are producing the maximum amount of cement now. In fact, cement is, again, as I said, it is the next material after water which is consumed by human being, and of course, India contributes to a large chunk in this production of cement. Okay, so that is what the production process is all about, cement production. Let us see the composition. Now, if we can quickly understand that there will be calcium oxide, because calcium carbonate burned to form calcium oxide. Obviously, I will have SiO2 and other materials available in clay, right, Fe2O3, and some fluxes which are added. So, they will also be there. So, the oxides, main oxides composition would be then alkalis, of course, then other impurities, etc., that would be there, magnesium oxide, that would usually be in, and they are controlled. So, some of them come from the ingredients, raw materials, some come through the process, and then the oxide composition are controlled depending upon the performance of the cement that you desire. Right. So, carbon dioxide from the lime is liberated while burning, therefore, calcium oxide and SiO2 would be there. And approximate composition limits of the ordinary Portland cement, if we look at it, generally calcium oxide would be 60 to 60%. Silicon oxide or SiO2 is 17 to 25%, and aluminum oxide is 3 to 8%. Iron oxide, it should be Fe2O3, the 2 should be subscript 0.5 to 0.5 to 6. This is controlled. Alkalis are 0.2 to 1.3%, SO3 is 1 to 3%. So, these are the oxide composition of cement. These are limits actually given, typical limits of oxides given, in most of the codes all over the world. The ordinary Portland cement will have this kind of limits of oxides. Now, these oxides actually formed into solid solutions and form some compounds. While clinker formation occurred within the kiln because they were partially melt, the main compounds those are present in cement are recognized as, these are the solid solutions. They are this compound 3 CaO SiO2, 2 CaO SiO2, 3 CaO Al2O3 and 4 CaO Al2O3 and Fe2O3, etc., etc. 4 CaO Al2O3 Fe2O3, this combined, this together, etc. These compounds, the names will come to them, but before that, since these are the compounds, and you can see they are complex compounds, actually complex oxides. So, therefore, we do not write in cement chemistry, we do not write them time and again 2 CaO SiO2, we abbreviate them. So, oxides are actually abbreviated in cement chemistry or in discussion with respect to cement, and CaO we abbreviate as C, SiO2 we abbreviate as S, Al2 we abbreviate as A, and Fe2O3 we abbreviate as F. Well, some more abbreviations are something like this, although it is not written here, but sometime we might be using is H2O we abbreviate as H, H2O we abbreviate as H. So, the compound water abbreviation. Similarly, SO3 we abbreviate as S bar, because S is already there. So, we abbreviate it as S bar. So, this 2 will come sometime later on, right. Now, if I use this abbreviation, then this compound can be written, as C3S. This compound can be written as C2S. So, C33CaO tricalcium silicate we call it, dicalcium silicate. I will come to the name I have not really mentioned to you, tricalcium aluminate. So, we call it C3A, and this is called tetracalcium aluminoferrite C4AF, tetracalcium aluminoferrite, and that is C4AF. All right. So, this is the abbreviated form of the compounds, and now onwards we will be using mostly this and surely not this kind of compound formation. So, let us see the name nomenclature. Main compounds in Portland cement, tricalcium silicate, this is this, and we abbreviate as C3S. We also, the mineral name is halite. So, it is a mineralogical name is halite. Dicalcium silicate, its mineralogical name is belite, and it is 2 CaO SiO2 or C2S. So, halite and belite. Tricalcium aluminate is 3 CaO Al2O3 or C3A, and its mineral name is aluminate. The blue colored signifies the mineral name, but its compound name is also tricalcium aluminate. Tetracalcium aluminoferrite. So, tetra calcium aluminoferrite, C4AF its abbreviation, and its mineral name is ferrite. So, alite and belite are the two compounds which has got silica, and aluminate and ferrite are the compounds where there are alumina and iron present, iron and alumina are present. Well, it is important then you control the properties of the cement, because their performance will depend upon, properties of the, control the composition of the cement, because performance will depend upon the compound composition. We will see that each compound actually behaves differently than the others. Although it is possibly, it is very difficult to actually identify directly C3S, C2S etc. in cement. If you take cement, identifying directly under microscope or something, or separating them visually, it is not easy, although you can identify them through, let us say, techniques, analytical chemical techniques. Now, their properties would be governed by the properties are governed by composition of C3S, C2S etc., etc. Now, therefore, there are some control ratios. Lime saturation factor is one of them. Lime saturation factor is one of them. Silica ratio and alumina ratio are the two others. So, we shall see that how they control. Lime saturation factor is defined in this manner. This is the calcium oxide divided by 2.88 SiO2, 1.2 A and 0.65 F, expressed usually as percentage. So, lime saturation factor is nothing but the ratio of calcium to some factor multiply some 2.8 multiplied by the silica content, 1.2 multiplied by the alumina and 0.65 multiplied by the iron Fe2O3, expressed as percentage. Silica ratio is S divided by S plus F, and alumina ratio is A by F. Now, how do they matter? If the lime saturation factor is greater than 100, you will have some lime which will remain uncombined, free lime. So, if it is more than 100%, right, this lime saturation factor more than 100%, then it results in free lime, uncombined lime will be there, calcium oxide, because you have now too much of lime in the system and it can't react. So, they will remain as unreacted. So, therefore, the compound composition of oxide that is present, proportion of oxides, various oxides, they are very, very important. Now, generally it is maintained from 95 to 98%. Lime saturation factor, it is maintained 95 to 98%. Higher silica ratio means more C3S. So, higher this means more C3S, less C3, C2S and obviously C3A. So, if you have high silica by silica ratio, you will get more of this compound, less of C3A and obviously less of C2S as well, as we shall see. Higher alumina ratio means higher C3A. So, higher. So, supposing I control these proportions, then I can control this oxide composition, I should be able to control the compound composition in cement, and that would result in different performance. So, depending upon performance or type of cement I want to obtain, I can control this control ratios in order to get appropriate compound composition of cement. Compound composition of cement is calculated from oxide composition by an equation called Boggs equation. Boggs equation, this is an empirical way of determining, and this is what it is. C3S amount is given as 4.07 C minus 7.60 S minus 6.72 A, 1.43 F and 2.85. This is SO3, S bar SO3, this is SO3, this is SO3. So, from this you can find out how much will be this. So, if you know the oxide composition then you can find out the C3S composition approximately using this Boggs empirical equation. C2S is obtained as 2.87 S, that is SiO2 content, minus 0.754 C3S. So, if you first calculate this, then from this you can find out C2S, and C3A quantity you can find out from 2.65 aluminum oxide and 1.69 iron oxide. C4AF is found out as 3.04 F. S of course is SO3 as I mentioned. So, if you calculate the compound composition from oxide composition, then C3S typically is something like 54.1%, and generally this is observed. C3A is 10.8%. If you take 65% from the oxide composition which I have given earlier I have given, from that if you calculate out, you can calculate out to find that C3S might come around 54.1, C2S might come somewhere there, C4AF will be there, and then minor compounds, etc., etc. So, you can obtain the compound composition from oxide composition using Boggs equation. This diagram shows you at different stages what are the SiO2, A, F, C, etc. Like this is limestone, then the shale, the mixed together as 80-20 proportion that comes to the mill, then the raw feed to the preheater and to the kiln. Final product is the OPC with 65% of calcium oxide, 3% alumina 5.6 and S 20.9%. So, this shows the stages, various stages, the composition of the oxide composition of the mixture at various stages. This is a phase diagram. In fact, if we see with temperature, the proportion by weight, then to start with I have got lime here, this is low quartz, right, and the clay minerals, iron oxide. Now, as my temperature increases, the water has gone out, 600, 800 degrees centigrade, carbon dioxide has gone up. So, mass would have reduced, total mass would have reduced, and C4F formation would have started here, C4F formation would have started here. This low quartz changes to high quartz, and here free lime started producing from about 700 degree or 600, below 700, somewhere close to 700, because lime would have broken down, calcium carbonate would have broken down, carbon dioxide would have gone. So, free lime would have formed, and as I go further, C4AF formation would occur around 1000, 1100 or 1200 degrees centigrade. C2, this would be, this is quartz, they will change, these are in some liquid state which will solidify later on. Belite forms here, and elite finally forms around 1400 degrees centigrade, which we showed earlier also, that about 1400 degrees centigrade C3S is formed, that is elite is formed. Belite forms earlier, and C4AF forms much earlier at around 700, 800 degrees centigrade. So, this is the production and composition of cement. Next is, you see, when cement reacts with water, it produces heat. It is an exothermic reaction, because philosophically we can understand this will occur. We have heated this material up, lime and silica, I mean clay and limestone, and therefore, finally, the product that is formed, it is heated and produced at high temperature. Now, this product will have some chemical energy locked up into it, because we have given energy to it, and therefore, it will have tendency to react, and it reacts with water, because that is what we have seen, that lime and surki reacts with water. Similarly, now we have produced it from the raw material of lime and silica, and this material, the clinker, grinded together with gypsum. Why gypsum? I will come to that sometime later on. It will react, with water, readily react with water, it will readily react with water, right. So, because it has got some chemical energy locked up, its chemical potential is high, it will readily react with water and give away those energy. So, the reaction is exothermic, reaction of exothermic, and the process, the reaction process we call it hydration process, because hydration, because it adds up water, simply it adds up the water. So, it is a hydration, in chemistry we call it hydration process, where water simply is reacting, right, getting added. So, it is hydration. Now, in the process of hydration of cement, heat evolution takes place. So, heat of hydration occurs, and if you see heat of hydration of this pure compound C2S, C3S, etc., we will find that C3A has got the highest value joules per gram, 867, or in calorie per gram is 207. C3S has got next highest as 502 joules per gram, and this has got 419, this has got least. So, the one which gives out maximum heat will have a tendency to react right in the beginning, earlier. It will react because it has the highest tendency to react. So, C3A has got highest tendency to react with water, C3S will have next highest tendency to react with water. This is a small compound, but this has the next tendency, and this is the compound which will have least tendency to react with water. So, this is what it is. So, heat of hydration is important from that point of view, and we will use this quickly. If you look now, cement, the elements those are present are oxygen, silica, calcium, aluminum and iron. Components oxides are calcium oxide, SiO2, Al2, Fe2O, 3 alkalis, etc., etc. Then cement compounds is the form from next stage is C3S, C2S, C3A, C4AF, and from this, by combination of this, we form various kind of Portland cements. Then this reacts and forms some product which we will discuss in the next lecture, right. So, summarize, if I try to summarize this, what we have discussed today. First of all, we actually introduced concrete as a material, and of course, together with it cement based composites, because concrete is one material, but today concrete is very, very versatile. With cement based composites, there are many of them, many varieties, as I mentioned earlier. So, we actually summarize them, introduce them by name only, not gone into the details, and we also explained, we also looked into that concrete is a composite made up of different materials, and the property of the final product is different than that, and also we stated that it is composite and it depends upon the level at which we are using. So, multi-level composites it is. At the highest level, of course, macro homogeneous, as we go it becomes a composite, next level, final level, it still becomes composites, etc., etc. Then we looked into the cement production process, we looked into the concrete material, looked into the cement production process, right. So, we looked into the components of concrete as well, natural aggregates, cements and cementitious, other material and water admixtures, and then we looked into cement production process, and then we looked into composition of cement. We will next follow in the next lecture we will look into the process of reaction of cement with water, which we call as hydration process, and the product that is formed both in physical changes that occurs, because cement and water, when you add together, it forms a plastic paste and then it solidifies as the reaction progresses, and then we will look into the product that is formed, hardened product, in the next class, right. So, thank you very much.